Hello everyone and welcome to another Teach Astronomy stream. Oh my gosh, I don't know if that echoed for a second. No, my desktop audio is off. I had my moderator view up and it totally just started playing myself a couple seconds behind. That's fun. Hello everyone and welcome to another Teach Astronomy stream. I hope everybody is doing well on this Monday morning or evening or whatever it might be for you. I know it's we've got a pretty international audience. I don't know if anyone's actually here yet, but that's okay. So today, if you didn't see from the title, if I didn't get it right again, because sometimes I forget to update it, but I think it's right this time, I'm going to be starting a book chat. So I had this idea back a little while ago when we were starting to come up with different ways to enhance the Twitch channel as we, moved over from our old setup to make it more worth everyone's time and more interesting to people instead of just having that one stream from Chris every month or every week. And I thought it would be really cool to read some of Professor Impey's books because he has a bunch of them. I think he's written himself at least 7 or 8, and then has a few others that he's co-authored or that he's edited, collections of essays that he's edited. Cool stuff. Lots of really, really good books, and you can, if you're interested in the other ones that he's written, if you want to see his whole biography is not the word. Right, the list of the books he's written. He's got a website as well. If you just search up Chris Impey, it'll come up, so you can check out those. But today, I wanted to start by reading his his newest book. It's not brand new, but it's called Einstein's Monsters. Here it is. Just make sure it's in frame. So it's called Einstein's Monsters: The Life and Times of Black Holes. I love this cover too. It's got this weird optical illusion thing going on with the eye and everything. It's very hard to point when you're looking at yourself on a screen and everything's kind of mirrored, but I'm doing my best. But so let's see, is there a description? Yes, perfect. So I'll start with reading the little book jacket description. The astonishing science of black holes and their role in understanding the past and future of our universe. Black holes are the most extreme objects in the universe, and yet they are ubiquitous. Every massive star leaves behind a black hole when it dies, and every galaxy harbors a supermassive black hole at its center. Frighteningly enigmatic, these dark giants continue to astound even the scientists who spend their careers studying them. Which came first, the galaxy or its central black hole? What happens if you travel into one? Instant death or something weirder? And perhaps most important, how can we ever know anything for sure about black holes when they destroy information by their very nature? In Einstein's Monsters, distinguished astronomer Chris Impey takes readers on an exploration of these and other questions at the cutting edge of astrophysics, as well as the history of black holes' role in theoretical physics, from confirming Einstein's equations for general relativity to testing string theory. He blends this history with a poignant account of the phenomena scientists have witnessed while observing black holes. Stars swarming like bees around the center of our galaxy. Black holes performing gravitational waltzes with visible stars. The symbol clash of two black holes colliding, releasing ripples in spacetime. There's more on the back, apparently. Clear, compelling, and profound, Einstein's Monsters reveals how our comprehension of black holes is intrinsically linked to how we make sense of the universe and our place within it. From the small questions to the big ones, from the tiniest particles to the nature of spacetime itself, black holes might be the key to a deeper understanding of the cosmos. Also, there's a picture of Chris in the back. That's my boss. Alright, so, I'm not sure if anyone's here yet. Maybe I'll reopen moderator view just for a second to see. Oh, there's 7 people here. Amazing. So if you're new, just as a heads up, because I don't know if I could see your usernames in the chat or anything, but this will be like a book reading sort of thing. But if you want to chit chat with me, I'll probably pause like at every page or two ish, um, depending on. Actually, they're broken up into all the chapters are broken up into pretty short sections. Like a page or two. So maybe I'll stop at every part there. Oh, you were looking at the book earlier, but you were worried it might be out of date. So, this book was written in, I think 2019. It was 2019. Also, sorry if you guys can hear the garbage truck outside. I'm not sure, but it was written in 2019. Chris published it then. And I think it's... there's definitely a chance that like some small things could be out of date because science continues on every day. But it's pretty up to date as far as the big stuff, because like it was only just a year and a half ago that it was published or so. So I think we should be good. I will ask Chris about that though. I'll ask Professor Impey before the next stream if he remembers writing anything that might have changed, because I personally am not like super I am not the astrophysicist that is Professor Impey's job, but so I wouldn't be able to tell if there were some things that might be out of date, but I will ask him and I will let you guys know next time, just so and I'll write it down so if we come across it in the book, we will know. But yeah, so welcome Poe and Fish and everyone else who's here. I'm glad you're gonna join me for this little adventure. So yeah, feel free to chat. If you can't chat, that's probably because you don't have a username yet. So feel free to go make one of those and come back. But yeah, so I guess we will. Amazon had it as November 2018. That's weird. That's very strange. Maybe they listed it before it was published, because this one does say first edition. I will look into that for you though. I'll make sure. Yeah, it definitely was before maybe this was this was Norton Company, New York and London. I'm not sure. I'll look into it. But yeah, this was definitely before the black hole image came out, I'm pretty sure. Because yeah, I think he finished writing it in 2018. And then, it has to go through the editing process, the publishing process, all that jazz. But yeah, so I don't think it'll mention the black hole image, but a lot of the science is still accurate and still the same. So with that, I guess we will start with, I can show you guys so this is it without the book jacket, because I cannot read things with a book jacket on it. I don't like it. But there it is, Einstein's Monsters. Cheers, yes. Yeah, for someone of my also limited knowledge, I'm sure it's pretty up to date. So that's our front page. These are other books by him, which I will probably read eventually. And then that's the cover page, which this image is, I don't know if it's a famous image or if I just always find it on Google, because I've definitely used it in several videos before, but it's a very cool image. Let's see. So there's a little, there's a little acknowledgement. So to Dinah, my love and inspiration, very sweet. And then there is a quote in the beginning, and it's from William Shakespeare's Macbeth. And it says, "Stars, hide your fires. Let not light see my dark and deep desires." And then we've got the chapter page. Getting that good flipping noises. Always fun. Okay. And there's a short little forward, so I will start with that. All right. Black holes are the best known and least understood objects in the universe. The term is used colloquially to talk about an entity that sucks in everything around it. Black holes appear on screen and in fiction. They've been co-opted by pop culture. A black hole is shorthand for something enigmatic, with a sinister edge. I call them Einstein's monsters, as a metaphor. They are powerful and beyond anyone's control. Einstein did not create black holes, but he developed the best theory of gravity that we have for understanding them. What most people think they know about black holes is wrong. They're not cosmic vacuum cleaners sucking in everything in the vicinity. They only distort space and time very close to their event horizons. Black holes represent a small fraction of the mass of the universe, and the nearest examples are several 100 trillion miles away. It's unlikely that they can be used to time travel or visit other universes. Black holes aren't even black. They emit a fizz of particles and radiation, and most are part of a binary system where gas falling in heats up and glows intensely. Black holes aren't necessarily hazardous. You could fall into the black hole at the center of most galaxies and not feel a thing, although you'd never get to tell anyone what you saw. This book is an introduction to black holes, large and small. Black holes are deceptively simple, but the math needed to understand them is fiendishly complex. We'll meet scientists who revealed black holes to humankind, from theorists who dared dream of stars hundreds of years ago to those who wrestled with general relativity and beyond. Black holes cannot be understood without Einstein's theory of general relativity, developed a century ago, which says that space and time are distorted by matter. In the extreme case where mass is highly concentrated, a region of space is pinched off from the rest of the universe, and nothing can escape, not even light. That's a black hole. But even Einstein was skeptical of their relativity. He was not alone. Many notable physicists doubted that they even existed. They do exist. Evidence has accumulated for 40 years that when massive stars die, no force in nature can resist the gravitational collapse of their cores. A gas ball 10 times the size of the sun crunches down to a dark object the size of a small town. More recently, it's become clear that the center of every galaxy contains a massive black hole, ranging in mass over a factor of 1 billion. Examining where black holes live, we'll learn about binary systems, where a black hole is in a gravitational waltz with a normal star. We'll see that the best evidence for any black hole is at the center of our own galaxy, where dozens of stars swarm like angry bees around a dark object 4 million times the mass of the sun. When the massive black holes that all galaxies harbor rouse from their slumber and begin feeding, they can be seen across distances of billions of light years. These gravitational engines are the most powerful sources of radiation in the universe. Recently, physicists have learned to see with gravity eyes by detecting gravitational waves. When two black holes collide, they release a cymbal clash of ripples in space-time that race outward at the speed of light and contain information about the violent encounter. A new window has opened onto black holes, and all situations where gravity is strong and changing. Gravitational waves provide unequivocal proof, if any were still needed, that nature makes black holes. Every 5 minutes, a pair of black holes merges somewhere in the universe, pouring gravitational waves out into space. We're far from knowing everything there is to know about black holes. They continue to surprise and delight. Black holes allow general relativity to be tested in new ways. Nobody knows if these tests will affirm the theory or lead to its downfall. There is vigorous debate over information loss in black holes and whether or not the information is somehow coded on the event horizon. Theorists hope that black holes may be the places where string theory can be verified, finally realizing Einstein's quest to unify quantum mechanics and general relativity. This book has 2 parts. The first covers the evidence we have that black holes exist. This evidence spans a range of black holes, from those not much more massive than the Sun to leviathans the mass of a small galaxy. The second explains how black holes are born and die. It also explains how black holes push our theories of nature to the limit. Along with the stories of black holes, there are personal stories, including some of my own, Chris's own, as a reminder that while science is dispassionate, scientists are made of flesh and blood, with all the flaws and foibles that entails. As I am covering research in a fast-moving subject, some results quoted here may not stand the test of time. Oh, there's a note to the poemfish question. Any resulting errors, omissions, or misinterpretations are mine alone. We can imagine that intelligent creatures on many of the trillions of habitable worlds in the cosmos have deduced the existence of black holes. Perhaps some have learned how to make them and harness their power. Humans are a young species, but we can be proud to be members of the special club that knows of black holes. Prof Impey, Tucson, Arizona. Alright, I'll take a little break really quick. DJ said, I read Einstein, His Life, and Universe a while back. Was interested in this book. Thanks for doing this. Of course. Thank you for being here. Also, hi, I like Bossa Nova. Thank you for being here as well. I'm going to take a little sip of my coffee. I got myself a coffee because I feel like book reading always goes nicely with either coffee or tea. And I didn't feel like tea today. Got a coffee from unnamed coffee company that won't sponsor us. And I don't want to give them free press. How's the volume for everyone? Is it sounding good? Let me know if I'm too loud or too quiet or anything like that. I'm used to doing this with a second person, so it's good. All right. Okay. I guess we will. So that was the forward, and we will start with Part A. Evidence for black holes, large and small. How did scientists arrive at the concept of a black hole? In this part of the book, we'll see how speculation started after Newton proposed his theory of gravity, and spread after Einstein articulated the implications of his theory of general relativity. Today, we know black holes have two key ingredients: an event horizon, which acts as an information barrier, and a singularity, or central point of infinite mass density. Many notable physicists, including Einstein himself, rebelled against such a bizarre state of matter. But others showed that a massive star core would collapse to a density from which particles and radiation could not escape. If theorists had trusted the beauty of the mathematics of general relativity, they would have had no reason to doubt the existence of black holes. But science is empirical, so astronomers labored to track down their elusive quarry. It was only with the advent of X-ray astronomy, a decade after Einstein's death, that researchers could see the hot accretion disk and twin jets that form when a black hole absorbs gas from the universe surrounding it. Hunting dark and dead stars is challenging. Even after 50 years of work, there are only 36 stellar corpses proven to be black holes beyond a reasonable doubt. They are the closest They are the closest examples of a projected population of roughly 10 million scattered in the Milky Way. As this evidence was being accumulated painstakingly, astronomers made the surprising discovery that massive black holes lurk in the centers of galaxies. When these black holes are consuming matter, they become the brightest objects in the universe. So they are not black, as we've said. Crazy. Just gonna throw in my commentary every once in a while. That was a little intro before the first chapter. Also, hi Parzival. Hope everyone's doing well today. All right. So, first chapter is called "The Heart of Darkness," which is a reference. You're barely late. We just started. We're just a couple pages into the. We did the intro and we did the forward. So the first chapter is Heart of Darkness, which is, I think, a reference to a novel, which is not my favorite novel, but it's an Joseph Conrad novel. I don't know. It's Conrad. Just a fun little piece of trivia for you. All right, so the Heart of Darkness. Scientists are optimists. They're impressed by the reach and predictive power of theories like relativity and natural selection. They believe that the rapid progress of physics, astronomy, and biology observed over the last few decades will continue, and that science will spread its explanatory tentacles even farther into the natural world. But what if this ambition were to hit an immovable obstacle? What if the cosmos were to harbor objects that resist our prying eyes? Objects that are ciphers? Worse still, what if these mysterious entities were predicted by our best physical theories yet? Worse still, what if these mysterious entities were predicted by our best physical theories, yet had properties that cast doubt on those theories? Welcome to the world of black holes. Also, if I stumble over anything, if you miss anything, if there are words that you'd like me to explain at all, because some of these are like big words, and I know not everyone is first language is English, please just let me know, throw it in the chat, I will go back to them. So, because I know I'm already stumbling over a couple things. Okay. An English clergyman imagines dark stars. John Mitchell was, according to his contemporaries, quote, a little short man of a black complexion and fat. It's not very nice. He spent most of his adult life as the rector of a church in a small town in northern England. Yet famous thinkers of the day like Joseph Priestley, Henry Cavendish, and Benjamin Franklin beat a path to his door, because Mitchell was also a versatile and accomplished scientist. His modesty and his quiet life as a clergyman have caused him to be neglected by history. Mitchell studied mathematics at Cambridge University, where he later taught mathematics, Greek, and Hebrew. He founded the field of seismology by recognizing that earthquakes travel as waves through the earth, an insight which earned him a place in the Royal Society. It was Mitchell who devised the experimental equipment that was later used by Henry Cavendish to measure the gravitational constant, the fundamental number that underpins all gravity calculations. He also was the first to apply statistical methods to astronomy, arguing that many pairs and groups of stars in the night sky must be physically associated rather than chance alignments. The clergyman was at his most visionary in proposing that some stars might have gravity so strong that not even light could escape. He introduced the idea in a 1784 paper with the unwieldy title, On the Means of Discovering the Distance, Magnitude, etc. of the Fixed Stars in Consequence of the Diminution of the velocity of their light, in case such a diminution should be found to take place in any of them, and such other data should be procured from observations as would be further necessary for that purpose. That's a hell of a title. That was me interjecting. Professor Impey did not write that. The gist of the paper can be explained in not many more words than the title. Mitchell understood the idea of escape velocity and the fact that it would be determined by the mass and size of a star. He followed Isaac Newton in believing light to be a particle, and reasoned that light would be slowed down by a star's gravity. He wondered what would happen if a star was so massive and its gravity so strong that its escape velocity was equal to the speed of light, and hypothesized many dark stars that were undetectable because light couldn't escape from them. Mitchell's reasoning was flawed, but only because he was working with Newtonian physics. In 1887, Albert Michelson and Edward Morley demonstrated that light always travels at the same speed, regardless of the Earth's motion. Not until 1905 did Einstein make this result the premise of his special theory of relativity, proposing that the speed of light doesn't depend on the local strength of gravity. Mitchell also erred in conceiving of dark stars as being 500 times larger than the Sun, but having the same density. Stars that massive don't exist. The extreme effects of gravity are only realized when the density is high, which happens when a star like the Sun has been compressed into a tiny volume. All right, that's the end of a little section. Just gonna take a drink and look at the chat. Everyone's saying hello. Oh yeah, Parzival has exams. Good luck, my man. Exams suck, but I'm sure you're getting through them all right. I have a question for you. Are you guys doing virtual exams this year? That goes for anyone. Is everyone, if you guys are working at all, are people working from home in other countries still? The U.S. is a hot mess right now. So I obviously work from home just because I've always worked from home for Professor Impey since I moved. But I used to have in-person jobs, and I've lost those because of COVID. Now we're mids, and then the semesters will be offline. Okay, end of semester project. Gotcha. Oh man, good luck. You had your final semester exams online. Yeah, a lot of places are doing them online. It's a process. My partner is a grad student, and so he's been dealing with trying to administer tests online, and it's a hell of a ride. But all right. So the next section is A Great French Mathematician Weighs In. A dozen years after Mitchell's speculation about dark stars, French scientist and mathematician Pierre-Simon Laplace wrote about the same topic in his book, Exposition of the System of the World. More celebrated than Mitchell, Laplace was president of the Institut Français, maybe, acted as an advisor to Napoleon, and became a count and later a marquis. Like Mitchell, he studied theology and was from a religious family, but the call of mathematics was louder than the call of God. Laplace was apparently unaware of Mitchell's work. In a 2-volume treatise on astronomy, Laplace makes brief mention of the idea of a dark star as he considers the gravity of a hypothetical star much larger than the Sun, in quotes. It is therefore possible that the largest luminous bodies in the universe may, through this cause, be invisible. Through this cause be invisible. That makes a lot more sense. A colleague challenged Laplace to provide mathematical proof of this, which he did 3 years later in 1799. His work was flawed for the same reason as Mitchell's. The densest substance known at the time was gold, 5 times denser than the Earth and 14 times denser than the Sun. It may have been hard for scientists to conceive of states of matter millions of times denser, as is required for a modern understanding of a black hole. Oh, there's a figure. Should we find the figure? Let's find the figure. Where are the figures? Oh no! Is it on the next page? Just right on the next page? Just right on the next page. So here's the figure. Is that hard to see? Is it focusing? Come on. This is upsetting. You know what I'm going to do? Okay, this is very hard to see. But for next time, I am going to take pictures of the figures and the photos in this book before we do it, and then I will have them pop up. I'm going to do that. That's an idea. I'm going to keep going for now, and then I'll check the chat in a minute. Laplace excised any reference to dark stars from later editions of his book, probably because Thomas Young showed in 1799 that light behaves like a wave, and it seemed unlikely that gravity could slow down a wave. The concept of black holes couldn't emerge fully without a new theory of gravity. Newton's theory is simple. Space is smooth and linear and stretches infinitely in all directions. Time is smooth and linear and flows into the infinite future. Space and time are distinct and independent. Stars and planets move through empty space governed by a force that depends on their masses and the distances between them. This is Newton's elegant universe. Richard Westphal, Newton's biographer and a brilliant scholar in his own right, said, quote, "The end result of my study of Newton has served to convince me that with him there is no measure. He has become for me wholly other, one of the tiny handful of supreme geniuses who have shaped the categories of the human intellect, a man not finally reducible to the criteria by which we comprehend our fellow beings." End quote. Yet even Newton's great intellect did not fully illuminate gravity. He couldn't explain how it operates instantaneously and invisibly across a vacuum. He admitted as much in his masterwork on gravity from 1687, Philosophiae Naturalis Principia Mathematica. He wrote, "I have not been able to discover the causes of those properties of gravity from phenomena, and I frame no hypothesis." Okay, that's the end of that section. Everybody was chit-chatting. Let's see. DJ says, I hate virtual life. I feel that. It's really getting to me. I mean, this is really fun, and I'm glad that I've found a way to interact with other people that really like astronomy, and this is a cool thing to do. But yeah, it's for someone who really likes to go out and do things with friends and stuff, it's been tough. Also, like I said, I had a couple other jobs, and they were in person, and one was at a company that has since gone under, and the other one is at a live theater, so that's not happening for a while. But let's see. Thanks for the confidence. Don't worry. Yeah. I'm just reading through what you guys are saying. Yeah, virtual schooling, virtual teaching, virtual working is a challenge for everyone, I think. Focusing is very hard. I definitely have been feeling that, especially if you work and like do your recreation in the same place. Because the setup that I have right now, sometimes I'll do my other work on here, which, like, you know, if I'm doing Twitch or something, it's like it's a live thing. It's easy to focus in. But if I'm doing regular work, I also play video games on this computer, and like trying to have that separation in your head is pretty tough. These recordings are going to be recorded for people who can't join live. So Twitch keeps them for 14 days. But if you guys want, I can also do the same thing that I do with Professor Impey's live streams. And I can upload them to our old channel on YouTube. It just takes, because of the agreements between YouTube and Twitch, I think I need to give it 24 hours before I upload this. But yeah, I will upload them so they will be there forever on YouTube, if that's what you guys would like. And then it totally is nice not having to drive back and forth. That's like the one really good thing, right? Is there's like no commute time. You walk into your kitchen or something. Which one is the old channel? It is Astronomy State of the Art. I can probably link it here. Give me 1 second. I'm going to do that really quick. Just so you guys can subscribe over there too. So then when these come up, if you miss any or anything like that, because the plan right now is to do them every week. It is the same one as the last YouTube stream. Yeah. I'll post it here just in case. Where is my channel? There it is. Your channel. Astronomy State of the Art. This should work. Let me know if it doesn't. I'll test it myself just to see. Yeah, it should work. So yeah, I'll put them on there, and I'll make a little playlist of them. I'll do different playlists for all the different books we do. Oh, what games do I play? I play a lot of the Sims series. I'm very into the Sims. I play a lot of Among Us with my friends. What else? I play Animal Crossing. That's not on the computer, but I play Breath of the Wild. I play Overwatch. Stuff like that. All right. So, next section is understanding the fabric of space-time. We also have a fun picture of Albert Einstein. I really hate how it's just not focusing. So like I said, I will take pictures of these for next time. I'll read ahead, take pictures, and then have them. It'll be fun. It'll be something fun to look at. Okay. Understanding the fabric of space-time. Albert Einstein, a 26-year-old clerk at the patent office in Bern, dismantled the Newtonian system. In 1905, Einstein wrote 4 papers that would change the face of physics. In one, he looked at the photoelectric effect, where electrons are released when light shines on a material. He argued that light acts like a particle, carrying energy in discrete amounts, called quanta. It was this work, rather than his most famous theories of relativity, that won him a Nobel Prize. Experiments by Thomas Young and others had firmly established that light manifests behaviors of diffraction and interference, so physicists were forced to accept that light is somehow both wave-like and particle-like. Another short paper presented the most famous equation in physics, E equals mc squared. This says that mass and energy are equivalent and interchangeable. Since the speed of light, c, is a very large number, a tiny amount of mass can be converted into an enormous amount of energy. Mass is like a frozen form of energy, which is why nuclear weapons are so powerful. Conversely, energy has a tiny amount of equivalent mass. Given this equation, it makes sense that photons are affected by gravity. A third paper laid out the special theory of relativity. The theory built on Galileo's idea that the laws of nature should be the same for all observers moving at constant speed relative to each other, and added a second premise, that the speed of light doesn't depend on motion of an observer. The second premise is radical, as a thought experiment will show. think we have another figure coming up. Hopefully that one will look good. You shine a flashlight at someone far away. They measure the photons arriving at 300,000 kilometers per second, the speed of light. Suppose you rush toward them at half the speed of light. They still see the photons arrive at the same speed, and not at 450,000 kilometers per second. Now, suppose you rush away from them at half the speed of light. They again see the photons arrive at the same speed, not at 150,000 kilometers per second. Light does not obey simple arithmetic. Light speed is a universal constant, and the implications of this are profound. Speed is distance divided by time. If speed is constant, then space and time must be supple. As objects travel very fast and approach the speed of light, they shrink in the direction of motion and their clocks run slower. Einstein's theory says that light is the fastest thing there is. So he also predicted that objects will get more massive as they approach the speed of light, increasing their inertia so they are never able to reach or exceed that speed. As remarkable as all this work was, Einstein was just flexing his muscles for his seminal achievement, the general theory of relativity. With general relativity, Einstein extended his ideas from constant motion to accelerated motion, and brought gravity into the mix. He began with another Galilean insight. The Renaissance polymath had shown that all objects fall at the same rate regardless of mass. This means that inertial mass, the resistance of an object to a change in its motion, is the same as its gravitational mass, how an object responds to the force of gravity. This was a coincidence and a puzzle to Galileo, but Einstein suspected it was key to a new concept of gravity. Imagine you're in a closed elevator stuck on the ground floor. You feel your normal weight. Anything you drop accelerates at 9.8 meters per second squared. It's a familiar gravity situation. Now imagine you're in a sealed box in space, which looks like the inside of an elevator, being accelerated by a spaceship at 9.8 meters per second squared. One situation involves gravity and the other doesn't. But Einstein realized there was no experiment that could distinguish them. So here is the figure. So essentially it's saying, so this is a little guy in an elevator, ground floor. And over here is a little guy on a spaceship that looks like an elevator. And it's what can I delete? I got distracted. Pars, what would you put in here? Oh. I mean, it's fine. If you guys want to follow along, there's a nice link now. I won't say anything. That's very nice of you to Dropbox it. But anyway, yeah, so this is what he was talking about. So this is the guy on the ground floor in an elevator. This is the guy in a spaceship. Both of them are accelerating at 9.8 meters per second squared, and there is no difference. So it says here, in general relativity, there's no difference between acceleration due to gravity and acceleration due to any other force. So someone in a rocket accelerating in deep space at 9.8 meters per second squared will feel as if they are experiencing Earth's gravity and not notice any difference. Makes sense. I will get back to the chat in a second. Here are two more situations. In one, you're trapped inside the elevator in deep space. Weightless, you float inside the elevator. In the other, the elevator is in a tall building, and the cable has broken, so it's plunging to the bottom of the shaft. Oh my. There is no way to distinguish these situations either. Gravity is indistinguishable from any other force. This equivalence principle is central to Einstein's theory of relativity. Despite the calamity implied by a drastic plunge in an elevator, Einstein said it was his happiest thought, that's in quotes, that a person falling would not feel their weight. Interesting happiest thought, Einstein. That was an interjection from me. Chris did not write that. Einstein's new conception of gravity was geometric. The equations of general relativity relate the amount of mass and energy in a region to the curvature of space. the flat and linear space of Newton, with objects contained within it, is replaced by space that's curved by the objects it contains. We have another figure here. So we can see, it's one of those classic images. I know it's hard to see here, but it's one of those classic images where you have the grid that represents space-time, and then the balls of like planets, or, well, they're stars. The balls of like stars distorting the space-time. Please wipe the camera. I don't know if it is the camera. I'll try it. But the lens is like in farther. I can't even actually touch it. I think it's just it can't focus. Kind of looks better from farther away, actually. You can see it like that a little bit. But yeah. Also, this one's a longer section, so I'm going to pause really quick and read the chat. Clean the lens. I know. I can't clean the lens. The thing is, like, the way that the camera is, like, this is a clean lens. I think it's just because it's not, like, the highest high-quality HD. It's, like, a 720. So it just doesn't have the best focus. DJ said they're playing point-and-click games these days. Point-and-click games are great. There's one called Monster Prom. It's like a dating sim, but it's like point-and-click. It's excellent. Cyberpunk 2077. I'm so excited. Talking about some of that. Thank you for the link. Yes, thank you, Parzival. I will leave it up. I think that's fine. Veritasium is a great channel. We actually are very inspired by Veritasium. Hello, I have problems in my relationship. Can you draw a card? Unfortunately, this is not astrology. This is astronomy. No worries. We're actually reading a book about black holes, if that's of any interest to you. It will not predict your future, but it could predict the future of the universe, because we will find out how black holes are formed and die and all that jazz. And that's really cool. So if you want to hang out, feel free. If not, I totally understand. Oh, you were just kidding. Okay, cool. Sometimes we do get people that are a little confused. And sometimes they'll stick around and sometimes they won't, but it's fine. All right, so we will continue. Where was I? There it is. Okay. So we just talked about the, space-time being warped, like space-time being curved. Space and time are linked, so gravity can distort time as well as space. Physicist John Wheeler, whom we'll meet later as the person who coined the term black hole, put it succinctly: matter tells space how to curve. Space tells matter how to move. End quote. Let's also hear it in the words of the poet Robert Frost, who had an ambivalent relationship with the revelations of relativity. In the sonnet, "Any Size We Please," he found the thought of infinite space terrifying, but took comfort in the curvature that described a black hole. This is the poem. He thought if he could have his space all curved, wrapped in around itself and self-befriended, his science needn't get him so unnerved. He had been too all out, too much extended. He slapped his breast to verify his purse, and hugged himself for all his universe. It's a very nice poem. Also, welcome. I think we have some new people here that were wondering what we're reading. Ice Monsters by Prof Impey. Yeah. And we just started, so. 3 of the effects of general relativity are particularly relevant for situations of dense matter, epitomized by black holes. First is the deflection of light as it follows the undulations of space-time due to concentrations of mass. This was the initial, classic test of general relativity, carried out in 1919, 3 years after Einstein published the theory. A team led by the great English astrophysicist Arthur Eddington measured the slight bending of starlight as it passed near the edge of the sun. It wasn't a very precise measurement, but the affirmation of relativity turned Einstein into a celebrity and vaulted him into the science stratosphere. In 1995, a more accurate measurement agreed with Einstein's prediction to 0.01%. A second effect is a loss of energy as light leaves a massive object, called gravitational redshift. Think of it as photons struggling against gravity. The effect was first measured experimentally in 1960. A closely related effect is time dilation, the prediction that clocks run slower when gravity is stronger. Time dilation was first detected in 1971, when an atomic clock was flown at high altitude and it ran very slightly faster than an identical atomic clock kept on the ground. In 2010, the time dilation was detected over a vertical separation of just 1 meter, which required a clock with the amazing precision of 1 second over 4 billion years. That's crazy. That was me interjecting. That was not what Chris wrote. Time dilation measurements also agree with predictions from theory to an accuracy of 0.01%. General relativity has passed all its experimental tests with flying colors. General relativity seems esoteric and remote from everyday life, but the GPS system would fail totally if time dilation was not included in the calculations. Locating a phone on the Earth to within a meter depends on extremely accurate measurements of orbiting satellites containing atomic clocks. Relativity calculations are done by the computer chips in your cell phone. Without these corrections, GPS would be off by 10 kilometers after 1 day. The effects of relativity are subtle in the solar system, and where gravity is weak. But we'll see that they're turbocharged when stars collapse and gravity is strong. That's really cool. That's so interesting. Oh, I like Bossa Nova. You just put a link in about the GPS system and how it's an example of real-world relativity. That's really cool. Thank you. I'll have to read it later. And then, that's the name of the book. Yeah, we're reading that book. Also, for people who are new, if you caught it a little late, feel free to stay. I'm welcome. But if you ever want to go back and hear the forward and stuff like that, this will be archived on Twitch for 14 days, and then we're going to be putting it permanently on YouTube. So, cool. Fun stuff. Okay. Next section. A singularity and a life cut short. That's sad. General relativity is an austere and beautiful theory. Einstein said of his creation, quote, "Scarcely anyone who fully understands this theory can escape from its magic." End quote. That's beautiful. But few people have the mathematical fortitude to come to grips with relativity. In its most compact form, a single equation relates the density of mass energy to the curvature of space-time. That's like 5-minute Shakespeare. The full performance is a set of 10 coupled, nonlinear, hyperbolic, elliptic, partial differential equations. The underlying mathematics is based on manifolds, complex multidimensional shapes that are to Euclidean space as an origami dragon is to a flat sheet of paper. Einstein worked out approximate solutions to his theory so that Arthur Eddington could set up his expedition to measure the gravitational deflection of starlight during an eclipse. He doubted that the equations could be solved exactly, but general relativity immediately attracted attention from the best minds in physics. One of those people made remarkable progress. Karl Schwarzschild was born in Frankfurt and became a precocious student, publishing 2 papers on binary star orbits when he was 16. Well, that makes me feel like an underachiever. He rose quickly to become a professor and director of the observatory at the University of Göttingen, I think. Though he was over 40 when World War I broke out, patriotism inspired him to enlist in the German military. He served on the Western and Eastern fronts and rose to the rank of lieutenant in the artillery. Schwarzschild corresponded with Einstein in late 1915 while enduring bitter cold at the Russian front. Quote, "The war treated me kind enough," Schwarzschild wrote, "in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." End quote. Einstein was impressed by Schwarzschild's exact solution to his equations and presented it to the German Academy of Sciences. However, a rare and painful skin condition called pemphigus prevented Schwarzschild from pursuing his ideas. He submitted a paper for publication in February 1916, was sent home from the Russian front in March, and died in May. The life cut short, as mentioned in the title of the chapter. What was the solution that Schwarzschild found? That escape velocity from the surface of an object depends on its mass and its radius. Mitchell and Laplace had speculated about the possibility of light being trapped by a large, massive star with the same density as the Sun. Schwarzschild realized the escape velocity could also reach the speed of light if a star like the Sun collapsed to a high density. His solution had two striking features. The first was that gravity collapses the object to a state of infinite mass density called a singularity. The second was the prediction of a gravitational boundary that would forever trap what was inside. This is the event horizon. A singularity and an event horizon are the two essential ingredients of a black hole. And then it references a figure. Where's the figure? Where's the figure? I want to show you guys black hole. Oh, there it is. Again, apologies. I know it's foggy looking. But this is an example. So this is the black hole, this whole thing. In the center there is the singularity, and the outside, well, I guess the singularity is the black hole part. And then the outside is the event horizon. And the event horizon is where light cannot escape. So I guess the event horizon is technically where the black hole, like, starts, and that's the black hole part. I'm gonna look at the chat real quick. Parzival said that one paragraph got me like crazy, like 1 second over 4 billion years. I know! That's insane. It's just crazy that we have like the technology to measure that. That's nuts. Science is wild and amazing. Another book. A most incomprehensible thing, notes towards a very gentle introduction to the mathematics of relativity. Very interesting. Thank you for the suggestion. I'll check it out. We have to take an accent law. Yeah, some of the words in here, there are some things like in different languages or that should be pronounced differently. Oh yeah, Parzival, for some reason I held your message because you said German. I don't know why. It's fine. I allowed it. But yeah, I'm doing my best. But yeah, if there are questions about what I said, or if you want me to look up something, let me know. Whatever. Professor is relativity's mathematics. I'm just reading one of these questions. So, first of all, I'm looking at MHZ Naraman. I think that's how you pronounce it. I see your question here. First of all, thank you. I am not a professor. But I'm just reading I'm just reading Professor Impey's book, but thank you. So you're asking, is relativity's mathematics formula part of the stochastic math, or is it differential equations? That's a great question. I don't know. So as I have said multiple times, I'm not the astrophysics expert. I'm the reading and Twitch expert in our group. But I mean, it was mentioned before that differential equations are a part of, the general relativity stuff. So I'm thinking it's the differential equation one. I can't confirm it. Yeah, a lot of people are saying differential equations is a huge part of this kind of huge part of it, relativity. So I think we're going to go go with that one. If you want to confirm, though, feel free. A Google search will probably explain it a little better than I can, to be honest. Somebody said tensors. It's part of it as well. That would make sense. All right. I'm gonna take a little coffee sip. The Lagrange fellow yeeted that topic. Like, gosh. Yeet. All right. Cool. So, next section. The master of implosions and explosions. Oh, that sounds fun. Okay. Einstein wasn't pleased. Both he and Eddington were convinced that a singularity was a sign of imperfect physical understanding. It made no sense for a physical object to have zero size and infinite mass density. Einstein's theory had created something monstrous. Other physicists thought Schwarzschild's solution was an esoteric curiosity. For a star like the Sun, the Schwarzschild radius, that is, the size of the event horizon, was 3 kilometers. How could a star that was 1.4 million kilometers across, over 100 times the size of Earth, collapse to the size of a village? Another wonderkind of physics was convinced it was possible. Robert Oppenheimer was born in New York and studied physics at Harvard. After getting his PhD, he traveled around Europe and steeped himself in the emerging field of quantum mechanics. His scientific interests were voracious. Among other accomplishments, he was the first to apply quantum theory to molecules. He predicted antimatter, and he pioneered a theory of cosmic rays. Along the way, he built the best theoretical physics program in the world at the University of California at Berkeley. Oppenheimer was a cultured man with a deep interest in art and music, who had studied Sanskrit and read philosophy in the original ancient Greek. He had a strong social conscience and left-wing leanings. Oppenheimer developed the tools for understanding nuclear matter and realized that astrophysics provided some exotic real-world examples. As a star evolves, it keeps a delicate balance between gravity, which is always pulling inward, and the pressure from fusion reactions, which pushes outward. The Sun is stable, and it has a constant size as long as nuclear reactions continue. When the Sun runs out of hydrogen fuel, it will collapse to a dense state of matter supported by a quantum mechanical force called degeneracy pressure. That's called a white dwarf. Indian astrophysicist, another one of those names that I might mispronounce, Subramanian Chandrasekhar, I believe. So Subramanian Chandrasekhar worked out that the gravity of a star more massive than the Sun could overcome the force of degeneracy pressure and collapse down to the density of a vast atomic nucleus. That's called a neutron star. In 1939, Oppenheimer and one of his graduate students wrote a paper called On Continued Gravitational Contraction, wherein, with a challenging calculation, they showed that an even more massive star will collapse until it reaches a density beyond any known form of matter. At the end of the massive star's life, a black hole inevitably forms. In 1942, Oppenheimer was tapped to lead the American effort to develop an atomic bomb. He assembled a dream team of talented physicists to work at a secret site in Los Alamos in northern New Mexico, in an intense effort aimed at gaining decisive advantage in the war against Japan. Oppenheimer was committed to the work, but showed glimmers of conflict. After witnessing the Trinity test explosion in 1945, he simply said to his brother, quote, "It worked." Later, he chose the famous words from the Bhagavad Gita, "I am become death, destroyer of worlds." After the war, Oppenheimer's politics led to his downfall. He was subjected to the humiliation of an anti-communist witch hunt and stripped of his security clearance. His reputation was never fully rehabilitated. But among other landmarks in his massive physics legacy, he had taken black holes from speculation to plausibility. And that's the end of a section. Oh my god, where are you finding these links, Parzival? Like, I'm just impressed. You should support authors, in general. I'm just gonna say that. But also, I totally understand that some people, myself included, cannot afford to always support authors. And if it's not at your library, it's hard. I did not buy this book. I had Chris send me this book. So I understand. So I'm not going to say anything. But also support authors when you can. Let's see. Didn't Dirac predict antimatter? I don't know. I can't afford everything either, my dude. Who's Dirac? Paul Dirac? Yes, he did predict antimatter. Huh. It does. Doesn't it? Interesting. Well, for something like that, yeah, I mean, there's definitely a chance that there might be inconsistencies in this book with some historical things, but I think that also might just be, attributed to the fact that, like, a lot of times people either, there are times in science and in, like, other things where either ideas are, like, formed at the same time in different places, and so it's the question of who got it first, who published first, stuff like that, or it might have just been an oversight on Professor Impey's part. So yeah, it looks like Paul Dirac did discover antimatter. I wonder if they were on the same scientific team or something. Maybe that was it. Yeah, exactly. Like, Tesla found versions of X. I mean, you can even talk about the, like, Tesla and, what's his name? Oh my gosh. Oh, invented the light bulb. Electricity and everything. Jesus, Edison, thank you! Yeah, Tesla and Edison, there's always this debate on, like, who created things first, or even with the history of the film camera being created. Actually, 3 people are attributed to creating a different kind of film camera at the same time: Edison, the Lumiere brothers, and a third who is often forgotten, and I feel bad because I have forgotten his name, but it's a very interesting history to look at. All right, so next section: coining the perfect term for the inscrutable. Physicists don't always get along. The greatest scientists are often highly competitive, and they are also passionate about understanding how nature works. I've witnessed fierce rivalries in my field, and I've flinched at the brutal words scientists sometimes use against one another. Usually best ideas are affirmed and hard feelings are set aside. But sometimes conflict is rooted in personality, as was the case with Robert Oppenheimer and John Wheeler, the man who coined the term black hole. Oh, and here's a picture. That's Mr. Wheeler. There he is. Okay. Wheeler was mentored by the great Danish physicist Niels Bohr, who instilled in him a habit of not just cranking through the equations, but also asking deep questions about the nature of reality as revealed by physics. He considered but decided against doing his PhD thesis work in Berkeley with Oppenheimer, a man only 7 years his senior. Wheeler spent most of his career as a professor at Princeton, where he mentored many of the best physicists of the second half of the 20th century. He deserves much of the credit for making the study of gravity a legitimate mainstream subject. In 1973, as he neared retirement, Wheeler and 2 former students wrote the landmark text, Gravitation, which physics graduate students still read today. On the same day in 1939 that Oppenheimer's paper on stellar collapse was published, Wheeler and Bohr published the explanation for nuclear fission. While over in Europe, Hitler invaded Poland. Ew. Like Einstein and Eddington before him, Wheeler rejected the idea of a singularity. For him, too, it was a violation of physics. At a conference in 1958, Wheeler gave a talk in which he rejected Oppenheimer's idea, saying, "It does not give an acceptable answer." A spirited debate followed. Oppenheimer was often intense, impatient, and personally aloof. Wheeler was earnest, engaged, and curious to learn about everyone he met. Wheeler said of Oppenheimer, "I never really understood him. I always felt that I had to have my guard up." Wheeler did come around to Oppenheimer's idea after computer codes used to model bombs showed it was plausible, and at a conference in 1962 he praised Oppenheimer's work. Oppenheimer, however, did not hear Wheeler's words of support, as he had chosen to stay outside the hall, talking to a colleague. Their animus was fueled by a major divergence of opinion during the war. Oppenheimer was the chief architect of the atomic bomb program that helped end the war, but after that he put his energy into non-proliferation. Meanwhile, Wheeler and Edward Teller led the effort to build the much more powerful hydrogen bomb, which they nicknamed the Super. Oppenheimer opposed them, saying, "Let Teller and Wheeler go ahead. Let them fall on their faces." But they did not, and Oppenheimer later bowed to their technical prowess, which made a fusion bomb possible. For his part, Wheeler became hawkish after the death of his brother in 1944 in action in Italy. He bitterly regretted that the bomb hadn't been developed in time to change the course of the war in Europe. That's sad. In a talk in 1967, Wheeler remarked that after you say, quote, "gravitationally completely collapsed objects enough times, you start to look for a better name." Someone in the audience, who has never been identified, called out, "How about a black hole?" Wheeler began to use it to see if it would catch on, and it did. Like the term Big Bang, which was also coined by someone who did not subscribe to the idea, black hole is colloquial yet accurate. In his autobiography, Wheeler wrote that a black hole, quote, "teaches us that space can be crumpled like a piece of paper into an infinitesimal dot, that time can be extinguished like a blown-out flame, and that the laws of physics that we regard as sacred, as immutable, are anything but." End of section. I don't know what you guys think of that little anecdote of the guy just yelling, "How about a black hole?" from the back of the audience, but that's excellent. I love that so much. That's citizen science right there. I'm going to look at the chat real quick. Edison is an Ilosa? Ilosa? Oh my god. I was like, what is an Ilosa? Is that a different language? Oh my god, it's a curse word. Backwards. You're right, he is. Newton created calculus to make others understand and comprehend his ideas, and that's why calculus came into the picture. No, don't do it, he said. It's fine. It's okay. It's family friendly enough where kids won't figure it out. I don't know if there's any kids listening to a black hole book being read, so it's okay. But yeah, I love the idea that it just proves, right, that like science is a team sport, and sometimes those team members are not even scientists, because somebody's got to be the one that like explains everything to the community. It's like what Chris does. I mean, he's an excellent scientist as well, but engaging with the community in the way of like figuring out what the colloquial word for a black hole will be is a black hole. Like, that's cool. That's the facts of Tesla, and some others are hidden by Russia. Yeah, the whole Tesla Edison thing is very interesting. There's probably a million books and documentaries and everything like that about it. So, yeah, check it out. That, and again with the Selva says sorry for upcoming paragraph in here. Gonna take a lot of space. Oh. Oh, you're good. Okay, I'm going to read this real quick. So Oppenheimer argues strongly against the proton being the negative energy electron solution to Dirac's equation. He asserted that if it were, the hydrogen atom would rapidly self-destruct. Okay. So that's very interesting. So it seems like is he talking about the positron? It's very possible. I think maybe. Yeah. So I get it's I mean again, it's like the kind of thing where like usually you don't develop crazy astronomical joke. You don't have those eureka moments just like from sitting in a room by yourself for years on end. You have it because you combine a lot of ideas with other people and stuff. So that's why it's hard sometimes to figure out quite exactly who said, yes, that's the thing. Like that's like when it's such a team effort sometimes. But that's really interesting. I like that. I'm gonna look into that more. All right, so next section is a genius struggles with gravity and disease. Stephen Hawking was another brilliant mind who took on the challenge of black holes. His story is so familiar we almost forget to be amazed. A diffident and mediocre student at school, he scraped a first-class honors degree after working no more than an hour a day for 3 years. Stricken by ALS, a degenerative motor neuron disease, at the age of 21, he was given 2 years to live. Yet, he was elected to the Royal Society at age 32, and to the Lucasian Chair of Mathematics at Cambridge University, once held by Isaac Newton, at age 35. He nearly died of pneumonia in the 1980s, which resulted in him losing his speech and being given his now iconic mechanical voice. A Brief History of Time launched him as a celebrity and sold over 10 million copies. By the time of his death in March 2018, he had outlived his original death sentence by more than half a century. He's a great dude. He was a really great dude. There's a picture of him. It's really hard to see. Again, but it's a picture of Stephen Hawking in one of the zero-gravity airplanes, I believe. Yeah, it's one of the modified Boeing 727s back in 2007 with some other NASA employees. That's cool. It really is a good photo. Oh. That's not his last photo, though. That was about 11 years before he passed away. So, he did a lot of cool stuff. He was a cool guy. All right. Those close to Hawking described a personality with sharp edges, but in physics, at least, he was the most brilliant and original mind since Einstein. In his PhD thesis, Hawking focused on a topic that most physicists preferred to avoid: singularities. As we've seen, the implication of a singularity at the center of a black hole caused even Einstein to doubt his own theory. In mathematics, a singularity is a situation in which a function has an infinite value. This happens all the time, and it isn't fatal. Mathematics has many ways to manipulate and deal with infinities. In physics, however, infinity is a big problem. For example, a theory describing liquids might predict that under some conditions, the density of a liquid becomes infinite. That's clearly non-physical and indicates a deficiency in the theory. Hawking wasn't so sure that singularities indicated a problem with general relativity. He formed a collaboration with the Oxford mathematician Roger Penrose, who was revolutionizing the tools used to study the properties of spacetime. In general relativity, spacetime can behave strangely. These behaviors are part of the theory and not signs of a fatal flaw. Spacetime can have folds, tears, edges, holes, creases, and be multiply connected, and Sorry. And be multiply connected and topologically complex. Topologically complex. That was a lot. I think just the wording of it confused me a little bit. But it's crazy, is essentially what he's saying. Lots of things. The general relativity landscape is wildly different from that of Newton's gravity, which is based on three-dimensional space that is simple and linear everywhere. General relativity includes the possibility of singularities. There are only two kinds of space-time singularity in general relativity. A singularity might be caused by matter being compressed to reach infinite mass density, as in a black hole. Or it might arise when light rays come from a place of infinite curvature and energy density, as in the Big Bang. The analogy for the first kind would be a flat sheet of paper with a hole in it or an edge. The second kind has no obvious analogy. Any particle traveling along the sheet of paper simply disappears when it encounters the singularity. Hawking and Penrose aimed for a general treatment. They stripped away as many assumptions as possible and proved a celebrated series of singularity theorems to show that singularities are inevitable in general relativity. In other words, they're a feature, not a bug. Every black hole must have a mass singularity, and every expanding universe, like ours, must have started with an energy singularity. Hawking used the cosmology example for his thesis, and it made him an instant rock star in the rarefied world of theoretical physics. Hawking then turned his attention to black holes. Along with two colleagues, he proposed that, like all other objects in the universe, black holes are subject to the laws of thermodynamics. By this time, the mid-1960s, a full solution in general relativity for a spinning black hole had been found, adding to Schwarzschild's earlier solution for a stationary black hole. In mathematics or physics, a solution is the set of values for variables that satisfy all the equations. It's a sign of how very hard it is to find exact solutions in relativity that only two have been found in 100 years. That's crazy. One of Hawking's black hole laws was that the surface area of black holes always increases. When matter falls into a black hole, the area of the event horizon grows. And when two black holes merge, the area of their resulting event horizon is bigger than the sum of the individual event horizons. This led to a new debate, with a startling conclusion. In 1967, John Wheeler suggested that black holes were very simple objects, which could be described by just their mass and their angular momentum. With his knack for a catchy name, he called this the no-hair theorem, hair being a metaphor for the details that characterize most physical objects. Jacob Bekenstein, one of Wheeler's graduate students, attempted to combine Wheeler's theory with Hawking's understanding of black hole surface area. Bekenstein argued that the area of a black hole was a manifestation of its entropy. In popular usage, entropy means disorder. In physics, entropy measures the number of ways atoms or molecules in an object can be rearranged without changing its overall properties. The no-hair theorem implied that black holes don't have entropy, but Bekenstein pointed out that nothing observed in nature was immune from the second law of thermodynamics. Entropy is always increasing, and black holes should be no exception. As thermodynamics is a foundation stone of physics, Hawking accepted Bekenstein's argument, but he was then faced with a puzzle. If a black hole has entropy, it must also have a temperature. If it has a temperature, it must radiate energy. But if nothing escapes from a black hole, how can it radiate energy? Hawking's answer to this conundrum stunned the theoretical physics community. He said that black holes evaporate. Here's how it works. In classical physics, the vacuum of space is empty. But in quantum theory, virtual particles are constantly being created and destroyed. They exist for tiny instants of time, allowed by Heisenberg's uncertainty principle. Normally, these pairs of particle and antiparticle, or pairs of photons, disappear with no effect. But close to the event horizon of a black hole, intense gravity can pull the virtual pairs apart. One falls in, and the other flies away and becomes real. This is how a black hole radiates energy. And there's a little diagram here. It's so hard to see, I'm sorry. But so essentially this is a box, right? And the event horizon is the edges of this box. And then these are creations. That's a creation of a particle-antiparticle pair. And when they get close to the event horizon, there's the chance that it breaks them apart, and so one goes into the event horizon, the other escapes, right? Or they both get sucked in, or they both don't. So there's this idea of like if the gravity is strong enough to split them apart, then one of them pieces out and it, like, radiates energy. Like they repel. Not quite repel. I think it's just like their individual, the force in between them that keeps them together is overpowered by the gravity of the black hole and the event horizon for one of them, because they're not both in the same spot, right? So it's super, super close. This would be a really tiny, tiny measurement, but like one of them gets pulled in and the other one does not fully get pulled in, so it can escape, and that the bond between them is broken. You know what I mean? I think that's what they're talking about. But yeah, so that's how they radiate energy. The energy needed to create the real particle comes from the gravitational field of the black hole, resulting in a decrease in mass. Okay. Riffing off Einstein's famous quip about quantum mechanics that, quote, God does not play dice with the universe, Hawking declared that, quote, God not only plays dice, but also sometimes throws them where they cannot be seen. That's fun. I like that. Okay. There is a description under this figure that I can read as well. I just realized. It says that black holes are not completely black. Virtual particle-antiparticle pairs are continually coming into existence and annihilating after a short period of time. According to a theory of Stephen Hawking, when this process occurs near the event horizon of a black hole, one member of the pair can escape, while the other is captured by the black hole. The effect is that black holes radiate energy and will slowly evaporate. Hawking radiation was controversial, but undeniably brilliant, and Hawking was soon elected a Fellow of the Royal Society. Unfortunately, the effects of Hawking radiation are extremely small for a star remnant the mass of the Sun, a mere 10 millionth of a Kelvin, far too small for an astronomical measurement. The evaporation rate is amazingly slow. It would take 10 to the 66 years for a black hole the mass of the Sun to disappear completely. That's so long. But the culmination of the process isn't dull. The temperature and the evaporation rate increase with the decreasing mass, so black holes disappear in an explosive crescendo of radiation. Black holes seem to be getting stranger and stranger. Physicists explored their implications even as they doubted their existence. In 1935, Albert Einstein and Nathan Rosen had proposed the existence of bridges connecting two different points in spacetime. A black hole might be at either end of this bridge, which John Wheeler dubbed a wormhole. General relativity also allowed for regions of spacetime that can't be entered from the outside, and yet allow light and matter to escape. These are known as white holes. A black hole region of the future might have a white hole region in its past. Wormholes and white holes have not been observed, but as Steven Weinberg once said, quote, "This is often the way it is in physics. Our mistake is not that we take our theories too seriously, but that we do not take them seriously enough." End quote. In popular culture, black holes became metaphors for death and destruction, but they also held out hope for transformation and eternal life, since time freezes at the event horizon and nobody knows what lies inside. As novelist Martin Amis wrote, Hawking understood black holes because he could stare at them. Black holes mean oblivion, meant death. And Hawking has been staring at death his entire adult life. That's deep. Damn. Okay, that's the end of a section. I'm going to check and see. What time is it? 11:27? Okay. Originally I said this was going for an hour and a half, but I do want to finish this chapter, which is actually not too much longer, so I'll probably go till noon. Let's check the chat. It is the famous quote. Another link. Oh, amazing. Yeah, so Parzival put a link explaining the virtual particle idea. So if you guys want to check that out, it's got some nice diagrams in it. Very cool, thank you. It's crazy he gave an inference of string theory. I know. Einstein, Rosen bridges are wormholes, right? Correct me if I'm wrong. Yes. So Einstein, Rosen bridges, John Wheeler dubbed them as wormholes. But yes, that's what they're talking about. Yeah, and again, wormholes and white holes have not been observed, but, you know, never know. A black hole wasn't, I don't think, technically observed until we got the picture of it, right? So, I mean, maybe, like, effects of black holes have been observed, but y'all know what I mean. Okay. I think it's just 2 more sections. Yeah. Alright. Let's keep going. Betting on black holes. Stephen Hawking was a good person to bet with. His wagers rarely succeeded. His first was on the cosmic censorship conjecture. In 1969, Roger Penrose proposed that singularities are always hidden behind an event horizon. With the exception of the Big Bang, there are no naked singularities. An event horizon prevents any observer from seeing matter get crushed to infinite density. Because a singularity presents big conceptual challenges for general relativity, physicists hoped that black holes always had event horizons. In 1991, Hawking bet 2 Caltech theorists, John Preskill and Kip Thorne, $100 that the cosmic censorship is correct and naked singularities don't exist. In 1997, supercomputer simulations showed that, under certain conditions, a collapsing black hole might lead to a naked singularity caused either by nature or perhaps by an advanced civilization. Oh, aliens. Kip Thorne is lit, yes. Hawking conceded, paid up, and gave his 2 colleagues t-shirts reading, quote, "Nature abhors a singularity." That's funny. That same year, Hawking bet Preskill that information was destroyed in a black hole. Thorne switched sides and joined him in the bet. Information, in this context, is related to entropy. High entropy means disorder and a small amount of information. Normal gas, for example, is highly disordered and requires just a few bits of information to describe it: density, temperature, and chemical composition. Black holes have enormous entropy, much more than the balls of gas that form them, and accordingly, they are described with even less information than gas. All we know is their mass and spin. However, one could, in principle, make a black hole in an enormous number of different ways, such as by crushing together gas or rocks, or maybe books and mismatched socks, but you cannot see that information from outside. Then, the black hole evaporates with the release of disordered radiation. What happens to all the information about what made the black hole in the first place? This conundrum became known as the information paradox. In 2004, Hawking conceded this bet as well. At a conference in Dublin, he reversed his earlier position and said that information could survive passage into a black hole, albeit in mangled form. It would be like burning an encyclopedia and finding in the ashes and smoke feeble remnants of the information in it. Perhaps a clever calculation could reconstruct the patterns of ink and text. Hawking preserved the tenets of quantum mechanics, but he killed off an earlier speculation that information might not only be preserved inside a black hole, but might also pass into other universes branching off from a black hole. He told the New York Times, quote, "I'm sorry to disappoint science fiction fans, but if information is preserved, there's no possibility of using black holes to travel to other universes." Hawking was alluding to the idea in cosmology where the precursor state to the Big Bang could have spawned a multitude of universes, adding the notion that black holes might enable information to flow between the universes. Making good on his wager, Hawking gave his friend Preskill an encyclopedia of baseball, from which, quote, information can be recovered with ease, and he called his initial claim of information loss his biggest blunder. I met Stephen Hawking briefly when I was a graduate student in the late 1970s. Okay, Chris really needs to talk about these things, because that's wild. I didn't know that. I worked for him for like 4 years. I didn't know that. That's crazy. Okay, anyway, we're going to continue with the book. I met Stephen Hawking briefly when I was a graduate student in the late 1970s. He was giving a talk on black holes in London in honor of his appointment as Lucasian Chair of Mathematics. Hawking was 36 and at the peak of his powers as a physicist. He'd been in a wheelchair for a decade, and his speech had deteriorated to the point where only a few family members and close colleagues could understand him. One of his students put his head close to Hawking's to be able to hear each phrase, then conveyed it to the audience. At the end of the talk, I remember having the powerful feeling that whatever obstacles I might come up against in my life or career, they would pale into insignificance compared to what Hawking had faced. 20 years later, my cousin and I went to see him give a public talk in a large auditorium in Cambridge. The lecture had been prepared in advance, and it was delivered by the speech synthesizer that became his trademark. Questions went slowly because he had to use one finger to pick out phrases from a bank of thousands stored on the computer. His puckish sense of humor was on full display. Someone asked, "Will we ever be able to use black holes to save humanity from destruction?" Hawking paused, then tapped on the keyboard. Quote, "I hope not." Another question. "Could someone survive falling into a black hole?" Slowly, he tapped his response. "You might. I have enough to deal with already." The true answer to the second question is that an unfortunate voyager falling into a black hole would not survive, as the stretching force of gravity would spaghettify them. Gravity falls off with the square of the distance from an object. For any compact object like a black hole, the difference in the gravity force between 2 points at different distances from the object can be large. This is a tidal force. At a distance of 3,000 kilometers, the stretching force will create an acceleration between your head and your toes about equal to the Earth's gravity. That's uncomfortable, but survivable. At a distance of 1,000 kilometers, the stretching force is 50 times Earth's gravity, so your bones and internal organs would be pulled apart. At 300 kilometers, still far from the event horizon, the stretching force is 1,000 times Earth's gravity, and solid objects will be destroyed. Spaghettification isn't like a child's game, in which someone pulls your feet and another person pulls your arms, or even like the medieval torture of the rack. Space-time near a black hole is being distorted, so you would be stretched at the level of muscle fibers and cells in strands of DNA. That sounds painful. This creates a paradox. The event horizon is a point of no return, an information membrane. Information can get in, but not out. If you could dive into a black hole carrying a digital clock and somehow avoid being spaghettified, the clock would seem to keep normal time as you plunged in free fall across the event horizon. Meanwhile, a companion watching you fall in would see your clock slow while your distorted image slowly approached the event horizon, until both you and the clock appeared to stop. Now imagine we toss a book into the black hole. This book. Not this book. He didn't write that. But maybe. It'd be appropriate. Gravity says it will cross the event horizon and the information will be lost. But to an outsider's perspective, the book never reaches the event horizon. Is the information lost, or is it stored somehow on the event horizon? There's one bet that Hawking was happy that he lost. His first bet with Kip Thorne in 1975. Hawking bet against the existence of black holes as an insurance policy. He hoped to lose, but if he won, he said he could console himself with a 4-year subscription to the British satirical magazine Private Eye. As we'll see in the next chapter, the high-energy source Cygnus X1 eventually proved to be a compelling black hole candidate, so Hawking conceded the bet in 1990. Kip Thorne's prize was a year's subscription to Penthouse. End of the section. Kip Thorne's cool. Yeah, I like him. Recently, the paradox was solved. Oh, was it? Logically, the unchained. Yeah, it must be stored as something, right? I would be, or it goes through the black hole and is distorted, but there? I don't know. It's very interesting. So sorry if you can hear my mouth noises. I guess I am reading, so this is all mouth noises. Cool. We have one more section. There's a proposal to find the hair. Oh, that's cool. The most famous paradox in physics nears its end. Let's see. Ah, so it can shed. Oh, yes. Okay. I think I do remember reading this. This is very recently, I think. Yeah, because of string theory and stuff. It's very interesting. Yeah, I can't read the article right now, but the one that Parzival just put in the chat, that sounds really interesting. It's from Quantum Magazine. You guys should look at it. Very cool. Excuse me. That's cool. Signs of hair. Yeah. That's really interesting. Yeah, there's always research that's still going on, and I think that's the coolest part. Like we were talking about in the very beginning, like this book was published a year and a half, 2 years ago, and that was even before we got the first picture of a black hole. That's before this new information about the information paradox. And just science just keeps on marching forward. But yeah, on that note, we will keep marching forward and do this last section. The golden age of black hole theory. After Hawking's landmark findings, the pace of black hole research has accelerated. Like I just said. We're currently in a golden age of black hole theory, with a blizzard of papers published every year. Physicists are trying to reconcile the smooth descriptions of objects in general relativity with grainy descriptions of matter in quantum theory. One of the biggest conundrums, as previously mentioned, is the problem of what happens to information at the event horizon. Hawking's theory of black hole evaporation reached into the toolkit of quantum mechanics. He originally argued that the radiation from a black hole is chaotic and random, and when the black hole evaporates, all the information contained within it is lost. This violates a core premise of quantum theory, which says that particle interactions are time reversible, so it should be possible to run the movie backward and recover the initial state from the final state. This collision between two highly successful theories of physics, general relativity and quantum mechanics, was considered to be a crisis by most physicists. In 1996, Andy Strominger and Qumran Vafa used string theory to reproduce Hawking's entropy and radiation. String theory is a decades-long attempt to unify the four forces of nature with a conception of matter not as particles, but as tiny one-dimensional strings of energy, existing in a space-time that might have 8 or 10 dimensions. String theory is more fundamental than standard quantum theory because it postulates a single entity that underlies diverse particles such as electrons, protons, and neutrons. It's also appealing because it's mathematically elegant, but it has been difficult to test. Still, it was exciting when the theory was shown to explain some important properties of black holes, because this was the first success for a microscopic theory of matter in the realm of strong gravity. Strominger and Vafa's research suggested that information really could be recovered from a black hole. Hey, that's what we were talking about. However, there is no clear agreement on how the information is preserved, or on what string theory can tell us about the nature of black holes. Plenty of top-tier physicists are working on this puzzle. One intriguing idea suggests that information is stored on the event horizon, in the way that a hologram is 2D information storage of a 3D object. If information about the contents of a black hole were somehow coded onto the surface, This would resolve the information paradox. So this, there's a diagram here. So if the, oh gosh, if this is like the black hole, it says that this little guy is 1 Planck area, this bigger guy is 1 unit of entropy, and you know the whole thing, the outside of the circle is the black hole event horizon, and it says the entropy of a black hole is proportional to the area of the event horizon. Entropy can also be considered as information. The minimum unit or bit of information corresponds to a Planck area, and it is determined by the speed of light, the strength of gravity, and Planck's constant. It is as if the contents of the black hole are written on the event horizon as bits of information. In 2012, a big fly was found in the ointment. Sorry. In 2012, a big fly was found in the ointment. The virtual particles responsible for Hawking radiation are entangled, sharing quantum states even when they're widely separated. Getting information out by breaking entanglement would release a torrent of radiation, creating a firewall just above the event horizon. Rather than an uneventful journey into the dark abyss, a Voyager would be obliterated by the firewall. But as seen from the outside, the Voyager would still be trapped on the event horizon like a bug on flypaper. Do they die or survive? Nothing can get out, yet nothing can get in. Researchers are still arguing whether firewalls are inevitable or not. This discussion illustrates the ebb and flow of ideas at the cutting edge of black hole theory. Let's leave the last word on the subject to Andy Strominger. In 2016, in a 2016 paper called Soft Hair on Black Holes, co-authored with Hawking, he argues against John Wheeler's no-hair theorem. I'm getting tripped up here. He argues against John Wheeler's no-hair theorem and identifies particles that may act as oh my gosh. It's been a while, guys. I've been reading for an hour and a half. Okay, I'm going to start that sentence over. In a 2016 paper called Soft Hair on Black Holes, co-authored with Hawking, he argues against John Wheeler's no-hair theorem and identifies particles that may act as the quantum pixels for information storage at the boundary of a black hole. It's still a work in progress. He admits, quote, "I've got a list of 35 problems on the board, each of which will take several months. It's a very nice stage to be in if you're a theoretical physicist, because there are things we don't understand, but there are calculations that we can do that will definitely shed light on it." End quote. Over the past 100 years, black holes have evolved from a monstrous idea, one that violates common sense, to a proving ground for the most cherished theories in physics. Black holes are like a gift from the universe. They have heft, but the contents of the box are hidden and enigmatic. Yet even the wrapping is fascinating to study. I am reminded of Mark Twain's sardonic remark, quote, "There is something fascinating about science. One gets such wholesale returns of conjecture out of such a trifling investment of fact." End quote. It's time to ask a pragmatic question. Do black holes actually exist? Dun dun dun! And that's the end of the chapter. Hell yeah, guys, we did it. I can't believe I read for that long. I was a little worried. Let's see what's that saying. It's proved. It's not proved. Does anyone know if things are proved? What is proving, even? Yeah, there's definitely several articles that people have put in the chat that are really interesting, so feel free to go back and look at those. I like Bossa Nova. Of course, I'm glad that you guys were here. I was a little worried that no one would be interested, but this was really fun. I hope you guys enjoyed it. When will I do this again? So my plan is to do this every Monday, same time, unless something were to come up, but usually my schedule is very open, so at least for the foreseeable future, it's going to be every Monday at the same time. For me, it's 10 a.m. I don't know what it is for you guys, but that's going to stay on the schedule, so just in case you ever forget, you can check the schedule. And like I said, this will be on Twitch for 14 days. It's supposed to be on for longer. We're affiliates now. I don't know why it's not letting us keep it for longer, but it will be there. And then I'm also going to upload this to YouTube sometime tomorrow, because I got to make sure. Solving information paradox would deserve like a dozen Nobel Prizes, so far no solution. Oh yeah, for sure. And yeah, I'll put these on YouTube. I'll put a link. I wonder if Twitch will let us put a link to a YouTube page. But if you guys want the link now, again, I can put it in. This should be the right one. That's our YouTube channel. I'll see if I can put a link in the about page or something without Twitch getting angry with us, because I know they're competitors. But yeah, so that was really fun. Also, just last notes for stream things. Like I said, I'll do this next Monday, same time. The rest of this week, I know I think we have a stream from Professor Impey. I'm not sure what day, actually. I can look that up if you guys want. But it's going to be on our other channel on YouTube. Let's see if I have that information. Yes. I think we're doing it tomorrow at 10 a.m. So same time this started. Tomorrow. Yes, tomorrow. On the YouTube channel that I just linked. I hope. But if you're part of the email chain, that'll be sent out. If you're part of the Discord, there will be an announcement on there. And then we have our regular Wednesday chat. Me and Michael will be talking about possibly exoplanets this week, I think. I think we might have an exoplanet guest on. And then Friday, we'll be doing our amateur astronomy. Will the one next week be on Twitch or YouTube? Chris's Q&A for this week is on YouTube. For next week will be on Twitch. All of my stuff is gonna be on Twitch. It'll be right here. Parzival said you're getting notifications like 20 minutes after. That's weird. Yeah, I can. So if you're part of the Discord, I usually post about 5 minutes before I do before we start anything. If you guys want me to post earlier, I can do like a twice post thing, like maybe once like half an hour before and then 5 minutes before. Unfortunately, our notifications, there's no settings as far as the like Twitch notifications work. It's just like if you guys turn them on or not. But yeah, I've heard that some people are having like weird notifications. On Discord too? That's annoying. Okay. Yeah, email notifications. Yeah, I will work on that. As long as I just want to make sure I will talk to Matthew about that, because Matthew does the emails. I feel like there might be a limit on how many emails he's allowed to send. But also, if there is, next week I can figure something out. You guys, I'll find a way for you guys to like sign up for another short email list, with just the people that are here for that want to hear about all the Twitch stuff. And then you guys will get the emails regularly. Because yeah, I agree. Some weird notification stuff has been going on. So we'll try to get on top of that. And then what else? Also, oh yeah, follow if you haven't already. That would be awesome. Then you'll get the notifications on Twitch. Sometimes they're 20 minutes late, as we've discussed, but at least you'll get something, and it helps us with their follower numbers. Also, I know we were just talking about before how like none of us have the money to buy the book, but we are affiliates now. So if you are interested in subscribing ever, or doing little bit cheers and stuff, that would be amazing. Eventually we're going to have subscriber only chats, not for everything, just for like special things, like once a month. And there'll be some fun things like that. And you also get some emotes. But yeah, it just really helps out the channel if you can. If you can't, I totally understand. I'm going to keep bringing you some cool free stuff. But yeah, I think that's pretty much it for today. Unless anybody has any questions about stuff before we go. But I think I answered everything. This video is best like for reading the book. Yeah, I think it's a good book to start with. It's like a fun the way that Chris writes is very good for this sort of thing, because his writing is very approachable for people that are not deep into the physics stuff. It's not like you're reading a paper, which is cool. So yeah, I guess I will wrap it up here. And thank you guys all for coming. I hope I see you next week. And if you missed anything, check on the channel. It'll be archived. All right. Have a good one, everyone. Bye.